HyDRA, a deterministic hydrodynamic polishing system based on a polishing tool entirely funded and developed at the Instituto de Astronomía UNAM, is presented. HyDRA is one of several modern deterministic polishing techniques that allow for computer-controlled finishing of complex optical surfaces. The HyDRA system is based on a hydrodynamic polishing tool that generates a variable density abrasive flow that makes the production of high-quality optical surfaces of diverse materials possible. These are some early HyDRA tool prototypes. The tool comprises several stacked operational stages that generate a grazing abrasive flow with a predictable zero-force erosion footprint on the workpiece that removes material. A recent innovation to this tool adds a switching capacity that allows the polishing action to be interrupted at will without losing the stability of the operating parameters. This further increases the versatility and performance of the tool, since it is now possible to polish only the areas where the surface needs correction. Pulsed polishing also adds several new polishing techniques to this method. These are some examples of the latest HyDRA tools. The tool to the right now has the capability to pulse the polishing action, which allows for the implementation of several exciting polishing features such as PWM, pixel polishing, tessellated polishing, and simultaneous polishing with multiple tools. The HyDRA tool belongs to the fluid jet polishing family. It is a non-contact, zero-force hydrodynamic tool that rotationally accelerates a slurry and air mixture and expels it tangentially onto the workpiece. It consists of several operational stages. An abrasive suspension composed of water and polishing grit is fed to the tool's first operational stage, where it is mixed with air at a controlled pressure in order to produce a variable density abrasive foam. This foam then enters the rotational acceleration chamber, where it is sped up to high revolutions per minute. The rotational energy of the flow then turns into radial velocity in a nozzle that forms between the tool's divergent output and the workpiece. In this way, the abrasive particles graze the workpiece in closely tangential trajectories. Thus, the polishing particles generate a shearing action that removes material in a ductile removal process. The drag generated by this radial flow forms a central low-pressure zone or vacuum surrounded by a high-pressure ring. As a result, the tool floats over the workpiece, exerting no net force onto it, since these regions cancel each other out. This poses many advantages in modern deterministic polishing, in particular the capability of polishing ultra-thin surfaces such as semiconductor wafers and optical membranes. This graph shows tool force as a function of tool distance. The capability of HyDRA to float over the workpiece is the most distinctive tool characteristic. When the tool is close to the surface, a repulsive force keeps the tool away from the workpiece, whereas at larger separations, a vacuum force suctions the tool towards the surface. There is a stable equilibrium position where the tool exerts no net force on the surface and floats freely over it. This separation is typically 300 microns. One of the central advantages of the HyDRA tool resides in that it can be adjusted to exert zero force on the work surface, while maintaining considerable removal rates of about 10 cubic millimeters per hour. The hydrodynamics of the HyDRA tool differ from the linear jet polishing tools in that, in normal incidence, classic jets, the pressure profile is represented by a Gaussian distribution, where the maximum is located at the jet's center. In contrast, the pressure distribution of HyDRA on the workpiece presents negative values at the footprint's center and is circumscribed by an annular positive pressure region. With this, the force on the workpiece can be adjusted to net zero force. Here, the tool's operational parameters can be varied such that tool bias can be set to obtain the desired influence function. Here, some of HyDRA's main polishing statistics are shown. The HyDRA tool is part of a complex polishing robot, consisting of a CNC positioning device, a fluid and compressed air control system, a slurry management unit, which stirs the slurry and controls its density, and a software package that obtains error maps from a series of interferometers and generates dwell-time or constant velocity PWM trajectories. These trajectories correct the workpiece figure depending on the selected method, either pulsed or continuous operation. The HyDRA tool is attached to a 5 degree of freedom polishing machine with force feedback, based on a large format Cartesian CNC with 2 additional degrees of freedom, tip and tilt, implemented by means of a passive hexapod. With this configuration, it is possible to generate and polish any surface geometry. Since feedback control keeps all polishing parameters constant, removal is exclusively a function of dwell time. In this way, figure correction depends on the trajectory followed by the tool and the velocity at each point along it, which requires that the CNC be capable of following 5-dimensional controlled velocity trajectories. Simultaneously, C-axis movement is controlled so that the tool can accurately follow the surface contour with zero force. Nanometric removal is accomplished with a load cell that regulates tool height over the workpiece. In order to accurately measure the surface, a scanning Fizeau interferometer, able to measure optics of up to 1 meter in diameter, was developed at our lab. The test rig was based on a classical configuration consisting of a transmission sphere, a null lens, and a flat mirror used for autocollimation of the test surface. The HyDRA Trajectory Planning Tool is a software package developed specifically for the HyDRA tool. It feeds machining code to a CNC or any computer-controlled positioning device based on the error map that has been obtained interferometrically. When only one HyDRA tool is available, the amount of material that is removed at each specific position is proportional to the dwell time. This dwell time can be controlled either by the speed of the tool along a given trajectory when the tool is operated in continuous mode, or by the width of the pulses when operated in pulsed mode. A main window presents the project name and grants the user the ability to go from error maps to machine coordinates in 4 steps: error map alignment, base trajectory, surface shape, and machine coordinates. To demonstrate the HyDRA system, we polished an 84 cm hyperbolic primary mirror to lambda over 10 RMS, 0.7 lambda peak to valley, in order to prove that HyDRA could deterministically tackle meter-class optics. This internally structured, light-weighted borosilicate mirror has a radius of curvature of 4,833 millimeters with a 1 centimeter thick faceplate. This mirror had previously been polished using traditional methods to around 2 lambda peak to valley. Surface measurements with our interferometer provided us with an initial 500 nanometer RMS error map. The previous classic polishing of the mirror induced a 50 nanometer print-through of the cell structure on the surface due to the thin faceplate, which was evident in our initial error maps. The mirror also initially presented large fallen edges of the order of 2 microns. The HyDRA tool used for this experiment has a 7 mm diameter footprint with a removal rate on borosilicate of 13 cubic millimeters per hour using a 2 mm raster pattern. Polishing of this mirror consisted of 3 iterations of 5, 4, and 3 10-hour machine runs for a total of 120 hours. The mirror was measured at the beginning of the polishing process to obtain the first error map and after each iteration, so subsequent error maps could be obtained. The progress of the surface correction process is presented, with the upper left image representing the initial surface figure, 500 nanometers RMS. The next 3 panels show the results of the intermediate iterations with 305, 125, and 62 nanometers RMS respectively. The C-scale in all 4 cases is the same. The finishing process was terminated after reaching 62 nanometers RMS over the entire surface, lambda over 10 RMS, 0.7 lambda peak to valley. A new HyDRA tool design has been developed which allows switching slurry flow without losing tool bias. Switching frequencies of up to 10 Hz and pulses as narrow as 10 microseconds can be achieved with this new tool. The ability to operate the HyDRA tool in a switched manner widens its overall performance and efficiency, adding new applications. This allows the use of polishing pulses that can be applied on a per pixel basis or in a continuous scan using pulse width modulation techniques. With this feature, dwell time can be controlled below the minimum attainable by a continuous action at the maximum CNC speed. Since HyDRA tools can now be pulsed, several polishing heads can be mounted onto a common arm, which moves at a constant velocity over the surface. Dwell time is then controlled using PWM for each tool, as required by the error map. We can also take advantage of the self-conforming capabilities of HyDRA in that it is not necessary to employ a positioning device to conform the parallelism of the tool to the surface. Only 1 degree of freedom per tool is required. Polishing efficiency becomes a function of the number of tools, and in the case of a matrix configuration, several polishing runs can be implemented into a single sweep, reducing polishing time. Thank you very much.